Okay, we're going to take a look at Chapter 15, Section 1. It has to do with sound. And remember, sounds basically are pressure waves that we can hear. Now, our perception of sound depends on the wave's properties, and we're going to look at some of the different properties of them. We want to, since they are waves, can we compare them to other waves that we've looked at? Yep. We're going to look at the physical properties of sound waves and how is that related to what we hear. What is Doppler effect and how can we use Doppler effect? A wave, again, is a disturbance of any particular thing that carries energy through matter, or could move it through space, or transfer energy without moving the matter. We have sound waves, which have pitch and loudness. We look at the loudness by the sound level, measured in decibels, and then we're going to look at Doppler effect. So let's get started. Sound waves, important part of our existence. We already know that we're familiar with the characteristics of sound, and knowing that we could make certain determinations. We use these characteristics to categorize the sounds that we hear. Sound, at the end of the day, is a wave. As the bell here in this video vibrates backwards and forwards, it pushes waves out. We'll try to take a look at this. Not real exciting, but it strikes a hammer, and then as the bell pushes, it sets up a pressure wave. When it's not pushing, when it pulls back a little bit, the pressure decreases, and then so we have a pressure wave followed by a decrease followed by a pressure wave. If they happen at a frequency that our ears are tuned in to hear, then we hear the bell ringing. If it's above or below our frequency, including really, really slow, we're not going to hear it. Again, the edge moves forwards and the air particles are driven away from it. The air particles bounce off the bell with a greater velocity. When it's moving backwards, the particles are bounced off with a lower velocity. Doesn't mean that there's no pressure, but it's just a greater pressure or lesser pressure. This pressure is about atmospheric pressure, this pressure just slightly above atmospheric pressure. The results of these velocities, changes in the forward motion of the bell in the regions where the air pressure is slightly higher than average, and then we basically can hear this high pressure, low pressure, and again, if it strikes our ears in the frequency that was within our hearing, then we can hear the bell. Collisions of the air particles causes the pressure to move backwards and forwards from the bell in all directions. So we don't just have a linear beam, we have a sound wave that's transmitted out. The waves move through the air and they're vibrating the air as it goes, or oscillations in the air pressure. The air particles collide, transmitting pressure to the next set of air particles away from the sound. The frequency is the number of oscillations of pressure per second, measured in hertz. The wavelength is the successive distance between each one. Here you see a pressure wave coming through the slinky. Here's a second one coming out. The wavelength would be the distance between the two. If we're measuring them using this kind of information, again, from the peak of one to the peak of the second one is going to give us a wavelength. Because the motion of the particles is parallel to the motion of the wave, it's a longitudinal wave. And the speed of sound depends on the temperature. We measured the speed of sound in the air the other day. As the temperature goes up, the speed actually increases slightly. So what we should have found was at 20 degrees Celsius, our room was about 19 degrees Celsius, we should have had a speed of someplace around 343, and some of you guys were really close with that. Speed of sound is greater in solids and in liquids and in gases. If you're underneath the water, the sound seems to come at you a lot faster. If you actually have one ear in the water and one above the water and somebody slaps the water, you'll actually hear the sound from the water before you hear the sound that's in the air. Again, depending on the type of gas, will also affect that. That's why when you inhale helium and you breathe it out, since the air molecules could move faster, they come out at a higher frequency, and it sounds like you're talking like Donald Duck. Again, solids will transmit the sounds even faster than water does. They can't travel in a vacuum, though. They have to have something to collide against. They have properties with other waves. One of the things is they can be reflected. We call these things echoes. Requires time for the echo to return to the sound. It can be used. We can use this distance between the source and the reflected object to do a number of things. If we know that distance, then we could figure out the speed of sound. If we know the speed of sound, we could figure out how far the object is away based on when the reflected sound comes back. The frequency that we're going to be, or the formula we're going to be using, is lambda equals velocity divided by frequency. We've seen this equation before. It still holds true for sound waves. So the sound detector converts sound energy, which is the kinetic particles, into some other form of energy. Most common detector we've run into every day is a microphone. The microphone consists of a thin disc that vibrates, and it creates an electrical signal. Now, the other common detector is our human ears. They basically receive sound waves. Once again, believe it or not, they're going to convert it into electrical impulses that the brain interprets. So the sound wave enters the auditory canal. Basically, the outer ear is just kind of there, kind of a trumpet to kind of guide it in. But the hearing all takes place inside. Here you have the tympanic membrane, or the eardrum, and it goes through the hammer, anvil, and stirrup, or malleus, incus, and stapes. It vibrates. The stapes vibrates the continues to vibrate the fibers, and they vibrate they vibrate the liquid inside the cochlear membrane, and depending on which of the hairs inside the cochlear membrane are being stimulated, it sends an impulse, a nerve impulse, to the brain, and that's how we hear higher or lower. You'll notice it gets smaller and smaller, so that means which part is actually able to be vibrated depends on the frequency. Tiny bones transfer the information into the cochlear, into the cochlea, and it's detected by vibrating the fluid. There's hairs inside the cochlea that receive this information and send impulses to the brain. And so the ear can detect over a wide frequency, enormous range of amplitude. In addition, we can distinguish between the qualities of sound. They discovered, first of all, Mercian and Galileo first determined that the pitch, basically the highness or the lowest of the sound, depends on the frequency of the vibration. For instance, a middle C vibrates at 262 cycles per second, or 262 hertz. The ear is not equally sensitive over all frequencies. For instance, about the lowest frequency, the lowest tone we can hear is around 20 hertz. The highest tone is someplace around 16,000 hertz. However, our sensitivity ears goes away as we get older. So older people could only hear about 10,000 hertz. If you remember a while ago on cell phones, they came up with that mosquito ringtone that supposedly young people could hear, but older people could not. It was vibrating someplace between that 10 and that 16,000 hertz, so about probably 12 to 14,000 hertz. And that was a theory, that way young kids could have their cell phones on and they could hear it ring and the teachers wouldn't hear it. By the time we're in our 80s, we actually are losing more of our sensitivity, and so that's why it makes it harder for us to understand speech. It's not just because we can't hear because of the loudness, but if we're losing frequencies, it will affect our ability to understand what people are trying to say. So the physical and or the frequency and the wavelength are related. by the speed of sound, and these are two characteristics. Another characteristic, however, that we're interested in is the amplitude, or how loud something is. In humans, we can detect loudness with the loudness then is the intensity of the sound as perceived by the ears. The intensity depends primarily on the amplitude of the pressure wave. We are very extremely sensitive to these pressure waves. We can hear amplitudes of less than 1/billionth of the atmospheric pressure, or of an atmosphere. In other words, 2 times 10 to the negative 5 pascals. On the other end, we can go up to 20 pascals. So that's about a factor of longitudinally about 6 times greater. And by that time, it's starting to cause us some pain. So the ears can only detect pressures, though, within certain frequencies. So if these pressure waves are outside of our frequency, we're not going to hear them. We can detect them because our ears might hurt, but for instance, when you go over a mountain pass and the pressure changes, it could change by thousands of pascals, but because it's changing so slowly, we're not getting of the frequency. And so we are going to talk about this in terms of measuring sound level. And again, it's a logarithmic scale. That means that a tenfold increase can cause a doubling of the sound. So we're going to measure this in something called decibels. We're not going to actually do the equation for decibels in this class. But so let's start with the lowest level. The lowest level is this pressure wave of 2 times 10 to the negative 5th pascals. We're going to call that 0 decibels. As we go up, it turns out that a tenfold change in decibel level, it means something is about twice as loud as the original. So from a whisper at 30 decibels, 40 decibels would be twice as loud, 50 decibels would be 4 times as loud. So we can kind of go between these conversions. From the casual conversation, again, twice as loud to 60 decibels, and by the time we get into heavy traffic, the traffic is 4 times as loud as a casual conversation. It also turns out that a 20-fold increase in decibels is related to a 10-fold decrease in the pressure. So exposures to loud noises in the form of music has been shown to cause the ear to finally lose its sensitivity, overstimulate the cochlea. It basically gives up trying to hear. Usually it's going to be affected in specific frequencies, particularly the higher frequencies. The longer you listen to, the longer the exposure, the worse it is. In other words, you can recover from short-term exposure, in a period of hours. However, if you expose yourself to it over long periods of time, could last days or weeks. Basically, 100 decibels is kind of where we feel that we're going to start causing damage. I think if we go back to the chart there, you'll notice that it says a rock concert is at 110 decibels. A siren's 100 decibels. So if you go to a rock concert, you're probably going to recover. If you play in a rock band, unless you're wearing hearing protection, you're probably going to start to, or if you're a roadie or something, you're probably going to start to have hearing loss over time. Just kind of unfortunate. Musicians losing their hearing, kind of unfortunate. Again, if you play really loud music through your headphones, you can achieve that 100 decibel level. If somebody else could hear your headphones, you're probably around that decibel. We can reduce the sound levels by putting cotton earplugs in our ears, about 10 decibels. Ear inserts are about 25 decibels. The ear muffs that I have, those hearing, the blue hearing protectors, will protect up to about 45 decibels. The loudness then perceived by the humans is not directly proportional to the pressure wave. The ear's sensitivity also depends on the pitch and the amplitude. Also, perception of pure tones is different from mixed tones. When we talk about a tone, whether we're talking about like a tuning fork just producing a single tone, or whether we're talking about a musical instrument that produces a mixture of tones. So let's take a look at this idea of Doppler effect, see if this one will work. I think it's narrated by Stephen Hawking's sister. Okay, so that's Doppler shift. Now we could actually do some calculations here. Depending on what's moving, if the source is moving, we have to take into account the velocity of the source. If the detector or the person hearing the Doppler effect is moving, we have to take that into effect. The frequency of the detector is equal to the velocity of the detector and the velocity of the wave divided by the velocity of the source relative to the wave. We could set this equation up with the velocity of the sound wave. D is the velocity of the detector. S is the velocity of the sound source. So the frequency at the source emitting this is Fs. And finally, the frequency at the detector is what we're interested in, whether it goes up or down. So the equation applies when the source is moving, when the observer is moving, or when both are moving. To solve a problem using the Doppler effect, be sure the coordinate system, set up the coordinate system so that the position of the detector is from the source to the detector. The sound waves will be approaching the detector if from the source if the velocity of the sound is always positive. For a source moving towards the detector, the positive direction, which results in a smaller denominator compared to a stationary source, and for a detector moving away, we end up in the negative direction, which increases the denominator, and so it will change the frequency. Similarly, if the source is moving away, if the detector is moving from the source, then again the delta D or FD decreases. So let's take a look at this. Got a trumpet player sitting in a car playing a middle C, and the car is traveling, the convertible is traveling at 24.6 meters per second. If the car is coming towards you, what would the frequency be that you would hear? We're going to assume that the temperature is at 20 degrees Celsius. Why is that important? Because we need to know what the velocity of the air is. At 20 degrees Celsius, velocity of sound in the air is 343 meters per second. So, if we take a look at what we're going to try to calculate, we got the person sitting in the car, We know what the velocity of the source is, or the car is, 24 meters per second. We know what the velocity of the sound is. Speed of sound, 343 meters per second. The detector, the person is standing still. Again, 343 for the speed of sound, 24.6 for the speed of the car. The velocity of the detector is the person's not moving. We also know what the original frequency is. We want to find out what the new frequency is. So how do we solve it? We're going to use this equation right here. Okay, the frequency at the detector is equal to the original frequency at the source, times the velocity minus the speed of the detector, and our speed's going to be 0, divided by the velocity of the material minus the velocity of the source. We can kind of rearrange things a little bit. If VD equals 0, and then we divide top and bottom by the velocity by just V, velocity in the air, then the numerator goes to 1, and the denominator, that V there, gets divided by V equals 1, and Vs divided by V is Vs over V. So this is our new equation. So now all we have to do is plug in the original frequency, the frequency, or the speed at which the source is moving, and the speed of the sound waves, are basically the 343. So we got the frequency, we got the speed of the vehicle, and the speed of air, or sound and air, and we have an equation. We could find out that the frequency is going to be higher. It's going to sound like it's going up. Once it goes past us, basically we we could plug that information into this, and we would find that the frequency drops. So measured in hertz, realistic, sounds good. And again, we would use it. We're going to use that equation. By the way, with that equation, you could just put in, if you don't want to rearrange it, just put the velocity in on top and the velocity on the bottom. It'll still work the same way. So if you don't want to try to do that manipulation, just put a 0 in for the VD, put 343 for the V, 343, 24.6, and it still works. Okay, so the Doppler effects then occurs in all wave motion, both mechanical and electromagnetic. It's not just a thing that happens with sound. Remember redshift when we're talking about solar systems and the Big Bang Theory and all that kind of stuff. So astronomers use this again to measure distant galaxies and how fast they're moving away from us by the Doppler shift. Physicians can use the Doppler shift when they're doing an ultrasound. And bats use it to navigate for their prey. And that's it.